Welcome to the Global Composite Expert webinar series hosted by cdmHUB. This webinar series is to examine the history, present capability, and future of composites with the goal of sharing the vast knowledge of composites that has been developed over the past several decades. This webinar series is initiated by the leadership of Composite Manufacturing Simulation Center at Purdue University. We are located in this beautiful building called the Indiana Manufacturing Institute. When life returns to normal, we hope to welcome you to visit us. We launched the cdmHUB in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. The cdmHUB provides a very powerful website called cdmhub.org for the community to collaborate and carry out this mission together. And we envision cdmHUB to be the premier resource for composite design and manufacturing. And this webinar series is one of the initiatives cdmHUB started as a service to the global composite community. This webinar series are made available by the support of cdmHUB sponsors, including Dassault Systems, Cytec Solvay Group, MSC Software, through Digimed, Modex 3D. We greatly appreciate their generosity and also contribution to cdmHUB. They invite more organizations to join them and join us to support cdmHUB's mission of convening and serving the global composite community. This webinar will be recorded and made available on cdmHUB, and an email will be sent to all attendees once the recorded video is available. And the presentation will last around 40 to 45 minutes, and we'll have about 15 minutes for questions and answers. All attendees will be muted. Please submit your questions through the Q&A box.
Thank you, Dr. Yu. I'm delighted to introduce Professor Anoush Poursartip as our inaugural speaker in the Global Composites Expert Webinar Series. He is an admired colleague whom I've known for over 2 decades. Anoush and I first met through his student and protege, Professor Pascal Hubert of McGill University, while Pascal and I were at NASA Langley Research Center in 1999. Professor Poursartip is a global scholar known for his intellectual integrity and his innovation in both scholarship and organizational enterprises. He's the founder of Convergent Manufacturing Technologies, the home of the software products for CureKinetics, Compro, and Raven. In 2012, he founded Composites Research Network at the University of British Columbia. His numerous awards include election to the Canadian Academy of Engineering, the Medal of Excellence for Composites from the University of Delaware, and the ASTM Wayne Stinchcomb Award of ASTM for outstanding contributions in research, engineering, and teaching the technology of composite materials. He's a World Fellow and Life Member of the International Committee on Composite Materials. Finally, Professor Poursartip has played an international leadership role in the advancement of composite science and engineering in academia and especially in industry. His vision for the future of composites enterprise is widely respected and followed by the global profession. We are delighted to have him as the inaugural speaker. Thank you very much, Professor Poursartip. We look forward to your lecture.
So it's a pleasure and a privilege to have this opportunity to talk to you about digital manufacturing and disruption of composites. I'd like to start off, obviously, by acknowledging that the work I'm presenting here has been performed by a very large number of students, colleagues, collaborators at UBC, CRN, Convergent, and partnering organizations. I particularly want to thank the close collaboration with Dr. Reza Vaziri and Dr. Joran Fernland, without which none of this would be possible. The Composites Research Network gratefully acknowledges the support of the Canadian government, the Boeing Company, Toray, Avcorp, and Convergent. Composites have clearly taken off since the mid-60s when carbon fiber was first introduced, and as such, they're an excellent example of application pull as a driver for innovation. As such, composites practice has outpaced composite science certainly in the early days, but I would argue even today. And so an observation that comes out of that is that our whole regulatory environment came into existence during those early analog days, and thus the major focus was to manage risk and uncertainty. So fundamentally, a safe design must be routinely producible and shown to be as such. So if we look at the current paradigm, what we have is an approach that's evolved over 50 years and is essentially an implementation of the fundamental materials engineering principle that process history leads to a microstructure that evolves until the end of the process, at which stage you have your performance properties. And in this case, we have a process where the raw material and the structure are transformed into the finished product together, and a process where we don't have the ability to track all the relevant parameters and outcomes during or after the process. So fundamentally, what we're trying to do is show materials equivalence between the test articles, which may be a little coupon, a subscale element, all the way to the full test final structure, to the in-production articles. We need to show chemical, physical, mechanical equivalence. And this actually becomes increasingly difficult with larger, more complex parts at higher rate and ideally lower costs, things we've been striving for the last couple of decades. As a result, manufacturing is seen as complex and fragile and has quite rightly been given increasing attention over the last 20 years. And again, successful manufacturing is a prerequisite for successful design. So how does this all play out in the digitalization of composites? One of the things we've been doing as a major area of research and development over the last 20 more years is processing and manufacturing science. And an obvious approach to capturing that scientific knowledge is in a usable framework as computational simulation. Similarly, digital sensing, automation are obvious improvements in a factory. And in 2020, I really don't need to introduce digitalization as a topic to this audience. So a couple of ways of looking at digital manufacturing. One, which is very popular at the moment, is a factory equipment-centric view, where you talk about the first industrial revolution being water power, steam power, mechanical engineering, and we have graduated all the way now to automation at the end of the third industrial revolution, and it is said we're entering the fourth industrial revolution, where we have cyber-physical systems, artificial intelligence, embedded systems, and so forth. So this is a very control measurement-driven view. A totally comparable and equal view is to take a science-based view, where the first revolution was empirical science. We moved to model-based theoretical science. We're now coming out of computational science and entering a world of big data-driven science, integrated computational materials engineering. So very much a design, materials, product-centric view. And obviously these two views must come together. And so we think of it in terms of a digital twin. The sort of current state of the art is that in the physical twin, we can sense with digital instrumentation, we can do some processing, and then we act using automation. Out of this comes product that goes into service. If we look at the virtual twin, here we have simulation. We have physics-based simulation where we're basically predicting the asset's state, but there's also discrete event simulation where we're actually tracking how the assets move around the factory. And in a perfect world, all of this would actually then be transmitted to those folks who do in-service simulation. Currently, the coupling between these two is relatively weak, but we are at the threshold of tight coupling. And this is really coming from the fact that we now have an explosion in the data sciences. So we have artificial intelligence, we have machine learning, we have formalized uncertainty quantification. And all of this leads us to a world of tight coupling and what I like to call scientific AI, which respects the fact that we can fuse together the different simulations, the science-based simulation and the AI of the Industry 4.0. A couple of comments to make about the virtual twin. The virtual twin description must be integrated across the factory. You have to consider all the steps in the process. Even if today we do not have the full knowledge, we should be putting in placeholders. The other one is that we should be using consistent science-based state variables across all the cells in the factory so we can propagate our understanding right across the whole factory. So let's very quickly visualize a simple composites factory. In a pre-preg factory, for example, we have incoming quality control on the material coming from our material supplier. We store it, we take it out, we lay up a part, we may lay up the final shape, or we may lay up a flat charge and then form it. We then transform it, if it's a thermoset, by curing it. We NDI it, we machine it, we assemble it, we inspect it, we ship it. In the early days of the virtual twin, the focus was on the autoclave. And this, of course, makes sense. This is the step at which you have the greatest change in the material and in the structure. And if we look at that, it is actually very effective both to explain, but also to even simulate, to look at a 1D drill through the thickness of the part. The in-plane dimensions are typically very large compared to the through thickness. Therefore, the through thickness dominates in telling you what the thermal response of a structure is during processing. And that thermal response lays the groundwork for all the other mechanisms that we care about. So what we have is convective heat transfer from the airflow above and below the tool and the part. You obviously have the tool, you have the composite itself, and you have consumables on the top. And the name of the game is to try to make sure that the part temperature history, which are the green lines here, so we're plotting temperature versus time, you want the green lines to be within your specification, which has an upper and lower bound. So you drive the air temperature of the autoclave with the blue line. The part lags initially. At some point, as the exotherm starts, as the cure starts and accelerates, you get an exotherm. And you need to make sure that you don't actually overshoot the air temperature too much. You need to keep everything within the bounds of what you said you would do. This has been understood and modeled since the early days of composites. A seminal archival publication is that of Luz and Springer in '83, and they really laid out how to do process simulation. They had 1D governing equations, they had no tooling, no equipment, set temperature, no heat transfer coefficient, but they set the scene. If we fast forward to today, nearly 40 years later, what we have is the ability to run 1, 2, 3D models. We can put in very complex material descriptions. A major advance is we actually represent the equipment and tooling, which plays a very big role in the response of the system. More importantly, we are fleshing out a complete systems approach to simulation. So what we now have is this concept where we have material state variable distributions, both spatial and temporal, for the part right across the whole process chain, and we track things systematically in terms of chemical, physical, and mechanical state variables. And the key is that we bring in the effective equipment and tooling at all steps. So at the end of this, we actually have a full state variable description that can be passed on to performance models. We can already pass degree of cure, thickness, volume fraction, residual stress. And if we go in and look a little bit more detail at this step, what we have, as I said, is a 3D solution to the problem with heat generation for the curing material. So we take the tool, we take the autoclave, we discretize that. We now have to give it material properties. The key one is the curing material. There are now very well established methods for doing cure kinetics models and other material property models, certainly for epoxies. So we do a large number of tests. We reduce that, we fit it with the appropriate cure kinetics model, and we end up with a virtual material. The key piece that is missing are the boundary conditions. We need to understand the heat transfer below the tool and above the tool. It's a very complex airflow at times. For that, we can do CFD analysis, we can do calorimetry, or we can do IR thermal imaging. I'm going to show you an example of IR thermal imaging. We happen at CRN to have 3 tools, which are fairly complex geometry with complex substructure. They're about 1.5 meters long. And these 3 tools have identical geometries, except one is CFRP, one is aluminum, one is Invar. What we've done with these tools is we've put them in an autoclave, and we've ramped up the autoclave temperature very fast. That causes the tool to start heating up, but lagging. And at an intermediate temperature, we abruptly stop the cycle, open the autoclave door, pull out the tools, and take an IR thermogram. What we see is, of course, that the tool has heated up, And the way it's heated up is a function of its thermal mass, and depending on its diffusivity, its thermal uniformity in terms of showing the substructure. So the CFRP tool, which is thermally light, has poor diffusivity. So it heats up fast, but with very low uniformity. It shows the substructure. The aluminum tool has intermediate thermal mass, but great diffusivity, so the substructure really doesn't show through. And the Invar tool is both thermally massive and poor thermal diffusivity, so again, the substructure shows through. If you run the CFD and you apply that, what you find is you can actually predict those thermal histories very well. If you then put the part on this, because you have good boundary conditions, you have a good material model, you can actually do very accurate Kehr kinetic simulations, so you can really predict the thermal history accurately. This is really quite well established now in the sense that if we look at leading industrial adopters of this technology, going back 20 years now, the Boeing company used the original UBC software written by two of our students to design the Kehr cycle for the 787 fuselage. And this was supported at that time by the recent company Convergent. If we fast forward some 10 years, what we find is that things have progressed quite a bit. Whereas with the 787, the autoclave and the tooling already existed, and what was left was designing the process cycle for the part. With the 777X, Boeing took it one step further, and they used CFD simulation as well as Compro simulation to design not just the part, but the tooling and the autoclave. And as a result, they designed a very efficient axial flow autoclave, which they actually patented. And now you have an ability to systematically, reliably cure a 30-meter long wing in a very efficient manner. We've actually been pushing this capability at the systems level past that autoclave cell, and we've been working on AFP, forming, and other pieces. I'm going to focus on forming today. So forming is a very popular method nowadays because it allows you to get a complex shape efficiently. The problem with forming is that there are a number of mechanisms that are vying to activate. And what we're trying to do is we're trying to get the shape without wrinkling. And so the problem you have is that you need to ensure that depending on the conditions of your material, which are driven by the temperature and the degree of cure and other process parameters, you need to ensure that you shear out the excess length that comes in due to the bending of the charge. So what we have done in our modeling is we've put in all the major physics: in-plane movement, interply friction, intraply shear, ply bending, tool-part interaction, and also debulk and consolidation. As we take out the gaps, we take out the air between the plies. The key thing is that all our material properties are driven by the thermal history, by the advancement of the cure. So we have the same state variables as we have elsewhere in our simulation framework. And so if I run the model at two different temperatures, so I run it at an optimized temperature where the material has low enough shear modulus that it will actually shear, and at a low temperature where it won't shear properly, what I predict is that in one case, I will actually get a good part, and in the other case, I won't. And of course, at the same time, I'm running the cure model, so I know that I shouldn't run too high a temperature as I don't want it to actually advance too much. If I actually zoom in and I look at some wire markers that we've put into the part, what we see is that the model actually predicts the shearing of the corner, the web, and the bottom corner very well. So these models are really progressing very fast and are starting to show value already. We, of course, can then take what we've done at this step and actually run it all the way through into autoclave consolidation. We've known for decades now that if you have a part on a convex tool, the pressure intensification thins the corner, or conversely on a concave corner, it thickens the corner by resin flowing into that. We've been able to predict that for a couple of decades now. What we can nowadays do is, on top of that, by putting in the correct shearing behavior and end boundary conditions, we can actually show that you'll get constrained fiber buckling due to the fact that as you consolidate, you create excess length in the in-plane direction due to the geometry. So we're at a point where we can see that physics-based simulation is coming together and is showing great value in the design stage. But how do we now start merging this with data-driven modeling? How can we create value there? So here, the key point to make is that in data-driven modeling, fundamentally, there is no theory. But what we have been doing is we've been working on the fusion of physics-based simulation and data-driven modeling through an approach called theory-guided machine learning, where you try to take advantage of the best of both worlds. This gives us the advantage of working with small data sets. And let us remind ourselves that our data sets will always be small. To give you an example, AI experts say that given 1 million data points, they can create a machine learning algorithm that basically doesn't need theory. It's really good. So if you're the Apple company making 140 million iPhones a year, that's 2 days production. If you're Toyota making 8 million cars a year, that's 6 to 8 weeks production. If you're the Boeing company making 1,000 airplanes a year, clearly this won't work. So theory-guided machine learning says, yes, we have physical data, but we actually have domain knowledge and we have numerical data. How can we use that to inform the feature transformation and actually the structure of the layers of the neural net? So let me give you a simple example. Again, I'm going to do a 1D drill. I'm going to have a tool. I'm going to have a part. I have as variables my part thickness, my tool thickness, and my heat transfer coefficients. And I'm going to use as my ground truth the numerical data. So we're going to train a classic ML and a TGML model using 5,000 numerical runs. And what we're going to look at is the exotherm, the amount of overheating, as a function of the heating rate to reach the hold temperature. We're going to train the model in the zone of 1 to 3 degrees C per minute. The dashed line is the numerical simulation. The red line is the classic machine learning algorithm. And the blue line is the theory-guided machine learning algorithm. What you see immediately is that in the zone where we trained the model, there is no difference between the two machine learning algorithms. They both do a great job. What becomes apparent, though, is that the moment we move outside the training zone, the machine learning algorithm, the classic one, blows up. It's classic brittle AI, whereas the theory-guided machine learning algorithm, because it has the physics in it, extrapolates well. So what it means is we can have TGML models which we can use with confidence over a large process window. How do we use these models? Well, Convergent has a thermal assessment plugin for CATIA, which is intended to help a designer at the conceptual stage figure out if their part is thermally producible. So if we actually take a representative wing skin with, say, 270 unique zones, and we try to run very quick 1D drills of this problem, what we find is that because at this stage there is no tool, no autoclave, no cycle predetermined, we have to evaluate a whole bunch of choices. And the problem is that even with 1D runs, this can take as long as 27 minutes. We might be able to cut it down to 5 minutes by taking some shortcuts, but the truth is that a designer won't wait that long. Yet if we run the same problem with our theory-guided machine learning surrogate, all of a sudden that 27 minutes, that 1600 seconds, goes down to 5 seconds, even for this complicated problem. So all of a sudden, we have a viable way of doing conceptual design very quickly. More importantly, this ties back to the full numerical simulation, so you have confidence in what you did. We can take it a step further. We can do some deep search and optimization. Cure cycle optimization is a big deal. Cycles take long. We're trying to go to shorter and shorter cycles. And of course, the optimization routine doesn't really care. It could use direct finite element polling, or it could use the surrogate. So what I'm showing you here is an example of a optimization of a cure cycle for a 10 millimeter thick Hexel 8552 structure. And what we're trying to do is shorten the cycle without exotherm. So the trick, and this has been well understood for a long time, is what you do is you heat up the autoclave really fast. That pulls up the temperature in the part quickly. But then just as the part starts to exotherm, you drop the temperature in the autoclave. You stabilize the part temperature. You bring up the air temperature, finish out the hold, then you cool down. If you do it using the FE polling, the optimization routine gives you a prediction of about 170 minutes compared to about 250 to 300 minutes for the classic cycle. If I run it with the theory-guided machine learning surrogate, we get a very similar answer, slightly different cycle. The key point is that the big difference between these two is that it took 14 hours to run the direct FE optimization and just 90 seconds to run the surrogate. Now, the key point is, having done this very fast optimization, we can confirm it by running 1D, 2D, 3D models to confirm that everything is consistent, as it should be. We can take the next step. We can move out of design and into production. So I'm going to show you an example of science-based data analytics of production data. Again, we're focusing on thermal compliance, which is a huge part of what is done on a daily basis. So again, every part has to show that it has met the heat up requirements and it has met the requirements for how long it spends in the hold so that it's actually sufficiently cured. Interestingly, often you also are not allowed to stay on the hold too long because you can actually start degrading some consumables. The problem is that most autoclaves run mixed loads. The response of a given tool is not a function of only the tool itself, but it's also a function of everything else that is loaded in that autoclave. And the autoclaves are typically loaded to the gills and run daily. At the moment, the baseline decision-making is in the hands of very experienced personnel who have accumulated know-how over decades. What I'm going to show you is how we can use science-based data analytics to perform these tasks. So what we're going to look at is 9 years of production data from one autoclave in one facility. This autoclave had over 4,000 runs, over 75,000 parts, over 200,000 thermocouple traces over those 9 years. The way the analysis is done is a very simplified lumped convective heat transfer representation where you have a lump mass representing the tool and the part. As a result, the equation is very simple. The rate of increase of temperature in the part is proportional to the difference in the air temperature and the part temperature. And that constant of proportionality is the heat transfer coefficient, which is unknown, times some tool parameters that basically the thermal mass of the tool and its surface area. So you can rearrange these equations so that you can actually evaluate the only unknown heat transfer coefficient. These simple models actually fit the data very well. You have here in blue the air temperature, the green is a thermocouple trace, one of these 200,000, and the red is this model fitted to it. From this, you can actually calculate the temperature rate versus this parameter up here, and the slope of this line is in fact the heat transfer coefficient. So we can do science-based data analytics on many tens of thousands of thermocouple traces very efficiently. What we can then do is start looking for patterns. And what we see is a very obvious, clear relationship between an individual part and how long it takes to reach the cure temperature. So here I'm plotting the normalized time to reach dwell as a function of the part type. Remember, every part has been made hundreds of times over those 10 years, those 9 years. And what you see is that thermally massive parts take longer to reach the dwell than thermally light parts. This allows us to scientifically decide how to avoid injecting a slow curing part into an otherwise fast curing autoclave run. But we can go beyond that. We can actually take those tens of thousands of thermocouple traces and look at the heat transfer coefficient distribution that was measured. The first observation is that the range that we get is quite broad, but is exactly what we would expect from everything that we have done to date. More interestingly, as we start looking at the distribution of heat transfer coefficients for different kinds of tooling, what we see is that there is a different distribution for Invar steel and aluminum tools. And this indicates that there's something different about these tools. It may be, we've already allowed for the thermal mass. So it may be the type of design, it may be the size, and this work is ongoing as we try to understand the nuances of what's going on. But now we're in a position to actually use science-based data production analytics. The next step is to bring in uncertainty quantification. And here, what we do is we incorporate uncertainty into our material models, and then we propagate these and other uncertainties, in particular the heat transfer coefficient boundary conditions, through our simulations. And I'm going to show you how we then assimilate it with in-production data. So traditionally, our materials have been deterministic. We have pure kinetics models of various forms, but they're always deterministic. What we're nowadays doing is we're evaluating non-parametric modeling approaches. And the team that is doing this work in particular likes Gaussian process regression, and they're enhancing it with empirical Bayes methods to actually bring in some of the physics so that we can extrapolate well outside the training data. But fundamentally, what we have is a situation where if we have data, the confidence is high, and where we don't have data, we have high uncertainty. Let me show you a couple of examples. What I'm plotting here is the degree of cure versus temperature, and I'm showing you 3 data sets. A slow dynamic ramp, where as the material is heated up, it starts to cure on the ramp because there's lots of time for cure to occur, an intermediate ramp, and a fast ramp. Overlaid on the data is this shading that shows the percent error of the prediction at a 95% confidence interval. So very purple means we're very confident, less than 1% error. And as we go out to the light shade, we're at 50% error. Well worth pointing out that if we didn't have that injection of some of the physics, the error out here would be even higher. But the key point is that where we have data, we have high confidence, and we have a quantifiable uncertainty when we're away from the data. We can, of course, add more data. And here you're seeing more dynamics. You're seeing some vertical lines. These are actually the isothermal runs, which of course show up on this plot as a vertical line. But you can think of time contours leading you up this vertical line. But again, the combination of dynamic and isothermals shows how we can create a process window with very high confidence, but with quantifiable uncertainty everywhere we are. So this now allows us to propagate uncertainty. So we take this kinetics uncertainty and we propagate it through a part thermal simulation. So what I'm showing you here is a laminate, a thick laminate, with, in this case, thick silicone bricks on each side. And what I impose is the air temperature, so that is known well. What has large uncertainty is the heat transfer coefficient between the air and the bricks. And of course, what we're actually trying to predict is the temperature in the middle of the part. So when we run this model with uncertainty, and the uncertainty comes from the material model and the air temperature heat transfer coefficient, what we get is a prediction that again shows us the amount of exotherm, but gives us a confidence band around it. And what we see is that actually, the moment the material starts to exotherm, our confidence goes down quite dramatically. Might not be something we want to see, but this is actually what's going on. The really good thing, though, is that we can actually put on more data by bringing in the information from a thermocouple which is in an accessible place. It might be a thermocouple on the tool, it might be a thermocouple on the surface. And this information, of course, is useful because that thermocouple is also affected by the heat transfer coefficient. And all of a sudden, the injection, the assimilation of that extra information gives me a lot more confidence, and therefore my error bands decrease quite dramatically. Conceptually, this can be further propagated through the whole process chain, thus making all simulations probabilistic. In all of this, a key issue is how to retain the physics-based simulation backbone. Everything I've shown you to date is about using our capabilities to influence current practice, be it in design, be it in current manufacturing. What I'd like to do now is take this a step further and look at manufacturing simulation to support the disruption of practice. So here, what we're talking about is maybe 2 levels of disruption. One is, for the same design allowables, can we open up the manufacturing window with confidence? In other words, can we say that we know that changing the process cycle does not change the material properties, hence the design allowables? The other one, of course, is something that people have been dreaming about for a very long time, which is, can we confidently link manufacturing simulation with failure simulation and perform end-to-end optimization, thus trading manufacturing criteria with performance criteria? I'm going to do an example of the first, but I'm going to go into prediction of a property which typically is not predicted right now. And what we're going to do is we're going to look at the influence of the temperature history on fracture toughness. As I've explained already, we're always imposing a temperature history on a structure. Understanding that you always have to go to the correct final temperature for it long enough is easily explained in terms of degree of cure. But why should we care about the temperature rate at which we hit that hold? It appears at times an unnecessary requirement. It may well be for simple first-generation epoxies, say, but I'm going to give you an example of a complex material which is a toughened thermoset and how the temperature rate actually matters. So the material we're going to look at is a Toray 3900-2 material, which is a toughened interlayer composite, which is used extensively in commercial aircraft. And so this material has an interlayer which is toughened with thermoplastic particles. And we're running it through a large number of cycles where we run it at an excruciatingly slow 0.1 C per minute, all the way to a very fast 7 C per minute. And we're going to look at the resulting microstructuring properties. We first have to understand what's going on. So again, we're going to look at this degree of cure versus temperature plot. The red line is a 7 C per minute cycle. So you get to temperature very fast. So the cure advance to the hold temperature is very little. It's of the order of 5%. And all the cure occurs during the hold. At the other extreme, we have the 0.1 C per minute cycle, where cure starts occurring on the ramp up. And by the time we hit a degree of cure of 0.4, we're only at 120 degrees centigrade. So the material is starting to harden on the ramp up. Well, another temperature that's really important is the temperature at which the thermoplastic particles devitrify, they become rubbery. So clearly one cycle is on one side of it, the other cycle is on the other side of it. We can actually draw a horizontal line at the gelation point. And so now what we can say is the 0.1 C per minute run is in this quadrant here. So the material is actually the resin. The matrix is hard when the particle starts to soften. Conversely, the 7 C per minute, the matrix is soft when the particle starts to soften. As a result, when we put these two pieces of information together, we can explain the microstructure we observe, which is that when we run the 0.1 C per minute, we have an interlayer that is thick and particles that remain spherical. Whereas when we run at 7 C per minute, the interlayer has thinned out, the resin has flowed out, and the particles have deformed because the temperature was high enough. But there's one more little nuance that we have to understand, which is that if we actually look at the crack surfaces of a mode 2 failure, what we actually see is that some fibers have actually migrated into the interlayer due to the process history. And this occurs for the thick interlayers, for the slow cycles. And what you actually see is that a few fibers migrate into the interlayer, and these are important because these are actually going to promote fiber bridging, which will promote the interlayer crack migrating into the intralayer. So there it is, zooming in, showing it to you. This does not happen with the thin interlayer because the interlayer becomes saturated and you can't get enough fibers in there for fiber bridging. What this means is that when we actually look at our crack surfaces and we digitize the amount of the interlaminar crack fraction, we see a significant difference between the 0.1 C per minute and the 7 C per minute crack behavior over about 50 millimeters of crack growth. And when we now correlate that with the measured propagation fracture toughness, what we see is that the properties match the microstructure. Where we stay in the tough interlayer, the fracture toughness is high. Where the crack, due to fiber bridging, is forced into the intralayer, the fracture toughness drops. So when we plot the propagation and initiation fracture toughness as a function of heating rate, what we see is that the initiation fracture toughness is constant, but the propagation fracture toughness is very much a function of the heating rate. But we can actually explain that in terms of the process history affecting the microstructure, affecting the fracture toughness. What this means is that not only can we pass degree of cure information and residual stress information and thickness and volume fraction, but we are on the verge of being able to provide other properties which really matter if we are going to understand how to open up cure cycles, how to pass information to failure models. But there's one thing left before we can do this with full confidence, and that is we need much more data. If you want to disrupt practice, you have to be very confident that you're doing that. And it's becoming increasingly clear that the amount of data we have, certainly in the open, semi-open literature, is insufficient. We've done a review of the thermal data in the literature on thick laminates, and we found some 27 experimental studies over the last 40 years. Now, we may be off by a factor of 2, but that's still not a lot. And many of these studies are actually incomplete in the sense that they don't have properly measured thermal boundary conditions. If we look at spring-in data for process-induced deformation predictions, we've been able to find about 1,400 individual specimen measurements. And here, what we have is, again, if we're off by a factor of 2, we may have 3,000 measurements. So again, not enough. Now, we know that there's a lot of data behind closed doors, but that's likely not of the best form to be fully useful either. So we really need to focus on the physical digital twin going forward. An interesting observation is currently we measure very little in the physical factory, and though Industry 4.0 advocates would say we should measure more, the value proposition needs to be justified. Although there's a strong research push to measure more, factory managers are reluctant to do so because of cost and risk. And paradoxically or perversely, compliance-based approaches discourage gathering data. So we've been engaged in a number of projects to generate significantly more data, provide a pathway to the sort of optimum digitalization of the physical twin. So one concept that we've been promoting is the idea of a digital learning factory, where we've been saying if medicine is teaching hospitals, why doesn't engineering have learning factories? This has led to the UBC Digital Learning Factory initiative, and we have a proof of concept project underway with the Canadian Digital Technology Supercluster, which is an industry-led consortium. And here we have work statements which match exactly what I've talked about today. In fact, the data that I showed you from that factory was done as a project under this program. And another one is one of our companies involved, Lamazoo. They're a visualization company, an AR/VR company, and they're taking converging process data and visualizing that with us. The other thing we're doing is we have a research mini factory concept where we have a proposal to build 2 model mini factories to make small but discriminating parts. So all the complexity of a full-scale factory, but at a fraction of the cost. So we can make literally hundreds of specimens. And then we want to destructively test these so that we can generate a big enough data set to have confidence in all the simulations at all stages of the life cycle. And again, we've laid this out in a way that has the same thinking, factory design, factory digitalization, factory of the future, so we can get short, medium, long-term value. In summary, manufacturing simulation has progressed significantly in the last 2 decades. The merging of integrated computational materials engineering and Industry 4.0 is an obvious step, but we firmly believe that physics-based simulation must form the backbone of a digital strategy for composites manufacturing, the scientific AI concept that I proposed. And this is particularly important if we wish to then link to failure simulation. There's significant opportunities to benefit from what's already been done in the short and medium term. And of course, lots more is being done both in research and in development of new technology packages. But there is a cause for optimism that we can, in fact, disrupt composites manufacturing and design, A, by opening up the specifications with confidence, likely in the shorter term, and then better still by confidently linking manufacturing and failure simulation. To do this, we need to keep working on this area of scientific AI and the generation of meaningful and useful manufacturing data sets, because we really do need to create confidence in this digital disruption. Again, I'd like to acknowledge the work of all the people who at UBC, CRN, Convergent, and partnering organizations did the work. Again, gratefully acknowledge the close collaboration of Dr. Reza Vaziri and Dr. Joran Fernlund, and the funding and support of the Canadian government, the Boeing Company, Toray, Avcorp, and Convergent. And with that, my presentation is finished.
We thank Professor Poursartip. My name is Jonathan Goodsell at the Composites Design and Manufacturing Hub, and I'll be asking questions from the audience. Again, if you have a question to ask, please enter it into the Q&A box, and we'll be reading those. We'll begin with some questions near the beginning. Back when we were talking about properties and convective heat transfer coefficients, Professor Poursartip, one question came in about how are the heat transfer coefficients evaluated and incorporated into the curing simulation as boundary conditions. Particularly, they were curious about, were those constant, were they closed form calculations, or just directly from experimental data? I know you touched on some of that.
The answer, of course, is all of the above. It depends how much effort you want to put into it. So we know that the heat transfer coefficient can be back calculated from experiments. We know that, of course, it's going to be a function of the temperature and the pressure, because that gives you the density, and the density appears in the Reynolds number. So you can run full CFD models all the way to back calculating it from experiments. So the answer is, it really depends what you're going to use the models for.
And I'll look and see if there happens to come along a follow-on question. While we're doing that, another question about forming process and the impact of layup. The question was, considering the forming optimization feature, is the simulation able to evaluate the impact of different layup orientations on the forming process?
Very much so. It's obviously an incredibly important parameter. And so in the evaluations that we have done, layup shows up as a very important parameter. So if you remove the culprits, which typically are these 0-degree layers in the direction of the forming, then wrinkling diminishes.
A couple of questions about the theory-guided machine learning. The first one was a comment or question really along, is setting up the theory-guided machine learning time-consuming, and if so, is it transferable to different part geometries, or does it need to be repeated for each new part?
It's certainly time-consuming, but not ridiculously so. And the validity of a training set, you have two choices. You can create a ridiculously large TGML model to cover an enormous zone, or you can actually segment it. And so from an academic perspective, you obviously just look at the principles of how you do that. But a convergent is creating basically a framework where you have lots of TGML models, and the software automatically uses the one that is appropriate for the subset of the process window that is used. So it becomes quite transparent to the end user. The end user, given that they have access to the material library, would get the full physics-based CureKinX models, say, as well as all the accompanying surrogate models, and it would be totally transparent to the user.
Another question along those same lines is, could you please comment on extending the theory-guided machine learning on 2D and 3D simulations? The number of parameters becomes quite large, and we talk about forming, for example. How many training points would we need?
An excellent question, and I actually don't have an answer for that. Those are the kinds of questions that everybody's asking, which is how would even machine learning scale as we bring in more and more complexity. So the only thing I would say there is that is why it is so critical to always keep the physics-based backbone, because that is the only thing that prevents the problem from just exploding out of control.
A couple of questions also about directions for the machine learning. Do you envision the use of IR thermography data in the theory-guided machine learning models for composites manufacturing?
You could. Certainly from an academic perspective, from a research perspective, you are looking at whatever methods allow us to get more confidence in what's going on. The IR thermography, the thing it does, which is really nice, is it gives us a very good understanding of in-plane thermal distributions which really matters, say, in that INVAR tool where you're getting cold and hot spots where the substructure shows through. Whether you want to do that in general, going forward as a standard practice, is less clear. In our work, at one end, we're doing a very sophisticated analyses because we're trying to show how it all comes together. And at the other end, we're trying to create best practices that can be practiced in industry. So I look at it as a dial, and you turn that dial to the left to be very accurate, but very expensive, if you will, and you turn it to the right to become very fast and practical.
Another question along those lines: do we have any research using TGML for resin flow in RTM, or has the majority of the research been focused on prepreg and autoclave?
At the moment, our focus certainly has been on prepreg processes rather than infusion processes. And of course, everything I've presented today has been rather selfish and about what we have done. I'm not actually aware of any other researchers using similar approaches, but this is a very fast-moving field. People are getting involved at a very fast rate.
So let's move. There's been a few questions about the UBC Digital Learning Factory. And so one question was, is this a physical location making physical parts, or is it purely virtual?
So the intention is actually to make it physical. A big part of the Digital Learning Factory vision is the generation of considerable amounts of data. So we are looking at it as the aspirational goal is in fact to build a small factory on our UBC Okanagan campus, where we have a lot of land, a lot of ability to build something of fairly large size. On the way there, we have this idea of scaling up from this sort of tabletop factory to that full factory. So the whole vision is to actually have a physical and a virtual one. And so it is a vision that combines both physical and virtual twins.
And there was another question about the factory. The use of the mini factory concept in the design of factories and companies is clear. How do you envision its use in the training of factory managers and staff?
Sorry, can you the training of factory managers in?
And factory managers and staff. How could it be used in training?
Oh, I think it's a huge part of this. One of my roles is I'm the co-director of the Composites Knowledge Network, which is a knowledge mobilization center funded by the Canadian government. And so digital education, digital learning, digital workforce education is a critical part of going forward. If we genuinely want industry to adopt digital manufacturing, education all the way from operators to engineers to managers, it's a critical part of that transformation. And if I look at my career, a big part of what I've done is, in fact, to help socialize these new ways of manufacturing with factory managers who, quite rightly, are very conservative because they live with the daily reality of running a production facility. So that's a great question and a very important one.
We'll shift to a couple of questions about failure here. One of them rather specific, but perhaps you have a general comment, and it's if manufacturing is somehow related to failure, then which failure criterion would be better in this case for a Varta manufactured composite?
I'm going to take the fifth on that one. That is a very specific question, and I'm certainly not the most confident to answer that.
Your examples about the mode 2 fracture toughness for toughened prepregs cured at different cure rates is very interesting. Could you please elaborate if all tested samples were cured respecting the temperature overshoot requirements?
Yes. Yes. We were very careful to ensure that other than the ramp rate, the rest of the cycle was within the specifications.
The question coming to cure, and we have just a couple of minutes left, so we'll only be able to answer a few more questions. But regarding the large autoclave loaded with several different parts and tooling, how advanced are the simulation tools to be able to predict those cure cycles?
So I think the question is, how good are our CFD models to predict randomly loaded autoclaves? So the answer to that is that at the moment, there is not enough data in general to identify what best practice should be and how good those simulations are. Again, one of the things is that as we transition from sort of anecdotal information where you've got one paper which says, look, we thermocoupled everything, we ran CFD, and if you run the correct CFD models, etc., everything works. That is the beginning. What really matters is when you hit the tipping point where you can essentially educate other people to do that standard practice. So I would say that right now, the ability to use CFD to accurately predict heat transfer coefficients is still at a low maturity level.
Professor Poursartip, we want to thank you again. I think with that, we'll wrap up the question and answers. We're about at the top of the hour. And I believe, Professor Wenbin, you may have a final comment to make as we close, and we thank you all for your attendance and participation today.
Yes, thank you, Professor Poursartip, for the great presentation and also very, very dynamic Q&A section. And Jonathan, thank you for monitoring time. Yeah, and also I appreciate all the attention the attendees gave to this webinar. And just to remind you that we have a series of webinars come out. So the next one is 2 weeks later from Dr. Ramesh Toreja. And please sign up on our website with this, and we will close this webinar. And thank you all for participating. Thank you.